Okay guys, let's get going. 4 compounds on the board. We talked about last time. We showed these have relationships to each other. These are 4 stereoisomers of, if the chlorine wasn't there, that'd be 2 butanol. Oh wait, there's 2 butanol. 3 chloro, 2 butanol. Every one of these has that name. Because they're all stereoisomers. Stereoisomers have the same exact name. The only difference between what goes in the front is stereochemical descriptor. Okay? Relationship between these. 1 and 3 were what? Enantiomers. You can see that. What was it? RS. R, and this was, oh, if those are R, well, I bet you a steak dinner, that's S and S. Because we kept the backbone the same, we just changed the projection. That is going to change it to the other. That's mirror image. Our mirror image of RR is SS. What was this? This must be RS. Relationship between these two. If RS looks in the mirror, it don't see SS. What does RS see in the mirror? SR. These two are what? Enantiomers. 1 and 3 are enantiomers. We've already said that. 2 and 4 are enantiomers. Enantiomers are also known as a DL pair. Because one of these rotates like one way and one of these rotates like the other way, equal and opposite. And thus one is D and one is L. We don't know which is which until we get the information, but we know one is D and one is L. Louis Pasteur called these optical isomers because they have different optical activities, optical properties, enantiomers. So what's the relationship between 2 and 3? Are they stereoisomers? Yeah, they have the same exact name, the same connectivity. It's just they're oriented differently. But they're not mirror images. And stereoisomers that are not mirror images are called diastereomers. Diastereomers is pretty much a default category, not mirror images. Diastereomers. Okay? Diastereomers, we know enantiomers have exact same properties, same melting point, same density, same molecular dipole moment. They just have different optical properties. Diastereomers, on the other hand, have totally different properties. A lot like cis and trans. Cis and trans is actually diastereomers. Very different properties. You saw with the bromination lab, one of them had melting point in the 100s, the other one in the 200s. We have more to say about this. Fischer projections. What could we call number 2? What would we put in front of this? Well, since the OH is on the 2 carbon, and that's R, you could call this 2R, 3S. You could do it like that. If we knew how 2 rotated versus 4, we could call it maybe D, 2-chloro-2-butanol. If we knew this was D, but I don't know that information right here. So that's another way we could call it. All right, Fischer projections. We drew one in a Fischer projection. Did we draw one in Fischer? Fischer projections, need to be able to do that. Very useful. Let's see. Okay, when I'm looking at this, let's make these methyls so it just clarifies. There's methyls on the end. When you're looking at the methyls in the Fischer, typically you put alkyl groups at top and bottom. We'll be doing that. But when you look at these methyls, how are they projected towards you? Or towards anything? They're going away. Top and bottom means they're going away. So the question is, with the methyls going away, what side are these heavy atom groups, these substituents? What side are they on? That's what we need to know. So let's look at this. First off, which methyl do we want to have at the top and bottom of here? I think we did like this. And so this was 1 and this was 4. It was 1 at the top and 4 at the bottom. So we're going to put this methyl at the top. With that methyl at the top and going away, which side's the OH on? Well, the way to do this is to stand over here with the methyl going away. It's going away from this carbon. The methyl's going away. And if I'm over here, and the OH is projected towards you guys, and I'm over here with the methyl going away, the OH is on my left. With the methyl going away, the OH is on the left. The yttrium hydrogen going the other way is over here. Now, let's look at the fourth methyl. With it going away, which side's the chlorine on? Well, we need to come over here. Keep your feet on the ground. In the future, we're going to put our feet in the air. That'll be wrong. Feet on the ground. Because when I'm looking at this, my feet are on the ground. With the methyl going away from this carbon, the chlorine is on which side of me? It's coming towards you guys, so that's my right. The methyl going away, the chlorine is on the right. And there this is in the Fischer. This is Roman numeral 1 in the Fischer. Okay, we said 1 and 3 were enantiomers. Well, first off, we said they're mirror images. They're certainly mirror images. But are they different? Everything's got a mirror image. How do we know 3 is different from 1? Where's Waldo? Because if 1 does not have a mirror plane, the mirror image is going to be different. Does compound 1 have a mirror plane right through it? Can you cut right through it anyway? Sometimes it's hard to see here. It's much easier to see here, trust me. And the planes will either be right through here or right through here. Is that a plane right through here? Can we cut it in half? No. Chlorine on one side, obviously no chlorine on the other. More often we're going to look for planes right through here. Okay, I'm going to draw it and then I'll probably erase it. But is that a plane of symmetry through the molecule? No, and you have to trust that this is a potential plane. You can get turned around here. See, we've already done some work to get it into this type of view. Now it's easier. Work with this view. No, chlorine, we have to have a chlorine here. That's not a mirror plane either. And that's it. There's no mirror plane in this compound. Thus, the mirror image is different. Thus, the mirror image is called an enantiomer. Okay? And what we have here is just like your hands. One of them is sort of right-handed, one's left-handed. Okay? 2 and 4 are also compound 4, Fischer projection. Methyl at top, methyl at bottom. Let's call that 1 and 4. We're doing, this methyl is 1, this one is 4. With the methyl going away, what side's the OH on? It's on the right. The undrawn hydrogen is over here. With this methyl going away, the chlorine is on the, also on the right. There's the Fischer projection for compound 4. You actually could have cheated. You got to know when you can cheat and when you can't. If you want to learn how to do it, you shouldn't be cheating. If you want to cheat, you can just take this one. You've already drawn this one. When we draw that one, we know the only difference is that the OH is switched. Well, switching it is going to basically mean draw it over here instead. And if you draw it over here instead, we'll have what we drew there. So that's kind of cheating then. That's where you do one, and then from there you do the rest based on the first one. We'll do some more Fischer projections when we redraw next time. But I think the reason I drew these two is because there's other terminology we can use here. When your high priority groups are on the same side in the Fischer, see here, looking at the groups on the side, this is typically with alkyls at top and bottom. These are your two high priority groups that are on the sides. When they're on the same sides, this is actually called a retro. A retro is the Fischer projection with your high priority groups on the same side. Don't get confused. With alkenes, See, this is an E, erythro. In alkenes, E means what about your high priority groups?
Opposite. But they're on opposite sides.
They're on opposite sides. Your alkene. Trans. Okay, so don't get it mixed up. And if they're on the same side of the alkene, that's the same side. It's the same side. Z. Okay, but here, erythro, okay, how I remember this, first off, let's look over here. This one, in the Fischer projection, the high priority groups are not on the same side. That's a difference in the two. And when they're not on the same side, that's called trio. How do you remember this? Well, I remember this because if you draw an E, you draw a line, and then you draw all the other lines on the same side. When you draw your capital E. Everything's on the same side. Okay? They're on the same side. On the other hand, when you draw a T, capital T, you put a line on one side, and then you put another line on the other side. So you have opposite. That's how I remember erythro and trio. Of course, let's look at the mirror image. The mirror image of 1 is 3. Everybody agree? Is 3 going to be erythro or trio? Is the mirror image of this going to be erythro or trio? It will be trio. Hopefully you see that. The mirror image of trio is trio. The mirror image of erythro would be erythro. Just like the mirror image of cis is what? UV cis. It's cis. Now you're cis. If you look in the mirror and you see trans, let me know because we're going to have a strange mirror or something. The mirror image of cis is not trans. The mirror image of cis is cis. The mirror image of trio is trio. The mirror image of erythro is erythro. Okay? But that's terminology that can be used to help identify your Fischer projections. We could also probably use that terminology here. This is number 2. Number 2 is that erythro or trio? It's a mirror image of 4. Yeah, number 2 is erythro. If we drew number 2 in the Fischer projection, guess what? It's going to be, real quick, you may not even choose to draw it, but that's number 2 in a Fischer projection. If you do it, you'll end up in it. Yeah? We know it's mirror images. You see how these are mirroring? They're mirroring the Fischer. Yeah, these are mirror images. These are enantiomers. That's erythro, but guess what? This is also erythro. Because the mirror image of erythro is erythro. So 2, that was 2, right? If this is 2. So 2 may also include erythro here in the name. But still, that doesn't tell you which erythro you're dealing with. So you would still need more. Okay? Let's move on to the next, and we'll see some of the same things talked about in the next one. But before I raise any questions here. The next one's going to have 2 OHs. All right. Can we erase everything here? I reckon. Let's start a little fresh. Let's change both of these groups to OHs. The compound is drawn there, it's both OHs. That's just a metal coming off that punch. So let's just change these. Now you may not be able to do this on the paper. Hopefully you maybe already drew them. Yeah? This here. Do the R and R still stand? Well, we didn't do anything here. Is this still R? Yeah, because this is still the high priority group, even though it's OH, just like chlorine is a high priority group. So the R and S still should be correct. Okay, let's look at the compound generically. By the way, I have a handout here, and we'll get them for alkyne chemistry coming up. Generically, how many stereoisomers possible with that compound? How many chiral carbons in the compound? It's 2 chiral carbons. So how many stereoisomers possible?
4.
2 to the 2 is 4. Just like the previous one. And we drew the 4. We talked about the 4. For this one, the same thing, 4. 4 isn't really. Because that 2 to the n is the maximum number. Sometimes you can have less than max for various reasons. But you can't ever have more than max. That's the maximum number. Is this really 4 different compounds? Let's look at them. What's the relationship between 1 and 3? Those are enantiomers. But hold on, again. First thing is they're mirror images. Check. We should know that. But are they really different? How do we prove that they're different? We want to look for Waldo, because that will tell us. Because if we can find a plane of symmetry, that means the mirror image is the same exact thing. Plane of symmetry. Do you see a plane of symmetry? Is that a plane of symmetry? It's hard to see. I recommend drawing in a Fischer projection, then let's look at it. Much easier to see. Fischer projection. Let's call this methyl 1 and that 4. So this one's at the top. We're going to do that. Fischer projection. Methyl 1 at the top, methyl 4 at the bottom. That means 4 is by the ground. That means here's the ground. Okay? With methyl 1 going away, what side is the OH on?
Left.
With methyl 1 going away, the OH is on?
Left.
Correct. Because for the methyl to be going away, I need to be standing over here. It might be helpful for me to show a model. There's our backbone. And we only have OH is red here. Here's our backbone. Methyl's in the plane. OH coming forward. This OH, also coming forward. Well, I can make it come forward just by doing this, right? No, because if I do that, it's going to make the methyl go out in the plane. The only way I'm going to do this, I've got to disconnect. I've got the wrong configuration. The alkane is in the plane of the board. Methyl, methyl. The OHs are both coming forward. There it is on the board. OH is coming forward, yeah? This is the methyl 1, which is going to be at the top. Okay? I'm drawing the little guy over here. All right? And I'm saying, if I look through here with the methyl going away, okay? The methyl going away, the OH is on one side. Let's come toward you guys. It's on the left. I'm just going to turn and let you see what I'm seeing over here. I'm seeing this. The methyl going away, the OH is on the left. That's exactly what I want to have here. The methyl going away, the OH is on the left. Okay? Now this carbon, with the methyl going away, what side is the OH on? Well, I can't stand over here because this methyl is coming towards me. Coming towards me. So I need to come over here and stand. Keep my feet on the ground though, and look through here. That is, there's the backbone. I need to come over here and stand. Now that methyl is going away. And with it going away from this carbon, this OH is on my right. And the undrawn hydrogens are going the other way. There you go. Do you see a plane of symmetry? Here, if I cut right through here, OH on this side and OH over here. But what about here though? Is that a plane of symmetry? Is this lower mirroring the top? No. OH here, there needs to be an OH here to be mirroring. It's not. There's no plane of symmetry. Thus, the mirror image is different. They're enantiomers. The mirror image is different, like your two hands. They're not the same thing. Much easier to see planes of symmetry. What's the relationship between 2 and 4? Are 2 and 4 mirror images? Are 2 and 4 mirror images?
Yes.
Yes, they are. The mirror image of RS is SR. They're mirror images. But are they different? Let's put 2 in a Fischer projection. I'm just going to cheat. The first OH coming from 1 is the same, so that means it's over here. The second OH has been switched compared to this, so that means it's over here. If you switch from R to S, you go from one side to the other. Disconnect. We can't rotate. We'll rotate later. This is compound 2 in a Fischer projection. What do you see about compound 2 now? Does it have a plane of symmetry? Yes, it does. Right through here is a plane of symmetry. There's Waldo right there. You see it? It's easy to see in the Fischer. Can you see it here? It's not as easy to see there. But we do see that that's potentially one because over here you got a carbon with a methyl and OH. Over here you got a carbon and a methyl and OH. So at least you have the same things, but are they oriented the same? Because you have the same things on this side of the line. But they're not oriented the same, and so they don't ever line up to give a plane of symmetry. But in 2, they do. And we have a plane of symmetry. What does that tell us about its mirror image, compound 4? It's the same thing. Compound 4 is the same thing here. If we drew a Fischer projection of compound 4, it would look like this. That's 2 and this is 4. Drawn as mirror images. Fischer projections drawn as mirror images. I mean, it has a plane of symmetry. But that's the same compound, just drawn twice. Let's look at compound 2 here. The backbone. Boom. This OH forward, but this OH is back. So I got to disconnect and change that. There it is on the board. Let's look at the other one. Backbone here. This OH back, as opposed to being forward, and this OH forward. There's compound 4. Here they are. I'm just going to rotate this red over here like this, and rotate these red over there like that. Here we go. That's them, 2 and 4. Are they mirroring each other in my hand? Yeah, same or different? Uh-oh, they don't line up. Well, hold on. Boop. Now look at them. All it took was just a turn, and they lined up. It's the same exact compound. Mirror images that are same exact compound. So, how many compounds are actually on the board? Only 3 on the board. This compound is just drawn two different ways. It's the same exact compound. Only 3. In this case, we have less than 3. This is a DL pair. That is a pair of enantiomers. This is not a pair of enantiomers. It's the same thing. Is the DL pair a retro or 3O?
3O.
Is this one?
Yes.
3O. This one you could call a rethrow. It's the same thing, call it a rethrow. But instead of calling it a rethrow, it gets another name. Because it's, well, let's use this term. Compound 1 is chiral, meaning the mirror image is different. Is compound 2 chiral? No. It's a compound that's not chiral, meaning the mirror image is not different. The mirror image is the same, so we would call it not chiral. But hold on, it's got 2 chiral carbons. This is a case where you can have chiral carbons, yet the compound as a whole is not chiral. We said in the opening paragraph, if you've got 1 chiral carbon, the molecule will always be chiral. But if you have more than 1, it may not always be chiral. And this is the case. When you have chiral carbons, yet the compound as a whole is not chiral, it's called meso. Or a meso compound. But meso. So we would refer to this as 3O and 3O, but this one we would call meso. Meso is a special type of a rethrow. Yes, it's a rethrow, but it's better to call it meso. I'll go ahead and tell you a little trick that I use sometimes in doing these is back over here. Is this a plane of symmetry? It could be because you got the same connected bonds on each side, but are they oriented the same? We said no, that's not a plane of symmetry between them. I knew that already because this was R and R. If it's a plane of symmetry, that's a mirror plane. That means this side is mirroring the other side. Is it? No, because the mirror image of R is not R. These are not mirroring. But guess what? Over here, it's the same on both sides. A carbon with a methyl and OH, carbon with a methyl OH. But are the sides mirroring? Yes, because the mirror of S is R. That's a little trick. If there's a mirror plane between the molecules, that should have S on one side, R on the other, in terms of your configurations. So that's a little trick there. Let's move ahead and see. Okay. Stereogenic alkenes, we talked about that. Alkenes in rings. Is that alkene stereogenic? Is that alkene stereogenic? Right now it's cis. Can you also draw a transversion of that compound? Be very difficult. How are you going to make a ring, a 6-membered ring like this? 1, 2, 3, 4, 5. What, a big bond like that? You can't. I don't know if this was mentioned before, but alkenes and rings cannot be stereogenic. Unless the ring is pretty large, maybe like about 10. Okay? 10 atom ring, the alkene could be stereogenic, and you could have possibilities of that. That's one thing about alkenes and rings. Typical rings, they cannot be both cis and trans. How many chiral carbons in the compound at the bottom? How many stereogenic centers? How many stereoisomers? That's the type of question. Anybody got an answer today? How many total stereoisomers possible?
128.
How many?
128.
128?
Yeah.
You got them all drawn? Is it 128? You confident? That's the type of question we've seen. Make sure you've been looking at that. Definition of diastereomers, we covered that. Epimers. Epimers. Let's look at the other handout. You will see Fischer projections again in biochemistry when you look at your carbohydrates. Carbohydrates can exist in open ring forms, or in ring forms. When they're in ring forms, you're going to be talking about chair conformations. When they're in open form, they're going to be shown in Fischer projections. The carbohydrate, if you're looking at 6 carbon carbohydrates, have 4 chiral carbons. Here we go, glucose. 4 chiral carbons in glucose. And the chirality is shown by Fischer projections. And so when you look at this carbon, you should be able to determine R and S there, because the configurations, the projections are implied, right? Things on the side coming forward, top and bottom going back, right? And so you should be able to determine R and S for every one of these. But you can have lots of stereoisomers here. And the stereoisomers have, your different names. Glucose is the most common, but you can also have things like lactose or allose. What's the relationship between all these sugars right here at the bottom? Are these enantiomers of each other, or what? For example, what's the relationship between allose and maltose? Are they stereoisomers? Yes, they're all stereoisomers. They all have the same things connected at the same spots, but the projections are different. They're stereoisomers. What type of stereoisomers are these two? What's the difference? Well, the bottom 3 are the same projection. And if you do R and S, the bottom 3 is the same. But here, we've switched. Here it's mirroring. We switched from R to S. Okay? So, are these two enantiomers? No, because an enantiomer, everything would be switched. If you're RRRR, your mirror image is going to be SSSS. Well, whatever this is, like, I don't know, R, and then SSS. R, SSS. But over here, it would be SSSS. Does that sound like mirror images? No. So what's the relationship between those two? Those are diastereomers. Diastereomers are going to have different physical properties. But these are also called epimers. Because if you just switch one configuration of many, that's called an epimer. It's just more terminology. Because epimer means they're pretty darn close, but one thing's been switched. Now, these are epimers. What about allose and mannose? Are those epimers? Allose and mannose, are those epimers? No, because two things have been switched. Are allose and mannose enantiomers? No, enantiomers would have to be where everything is switched. Are any of these enantiomers of each other? The answer would be no. If you look at them, none of them are enantiomers. These are all diastereomers. But an epimer is a particular diastereomer where only one center has been changed. This starts with a carbohydrate that only has one chiral carbon, then you can go to 2, then to 3, and then to 4. Okay? But look at the two carbohydrates that have two chiral carbons. One of them is called erythros, and the other is called threose. In erythros, the two OHs are on the same side. In threose, the two OHs are on opposite sides. Because of that, that's where the erythro and threo terminology came from. So we can use it for any compound. We call it erythro or threo. It came from that nomenclature. Okay. The other thing is there, whenever you see capital D and capital L, that is not the same as little d, little l. Okay, that means something very different. I'm not going to go into that. There is a difference between capital D and little d. We're only using little d and little l. That means the way the light is rotated. Okay? So that was carbohydrates. We will certainly see that later. Any questions at this point? Let's see where we're at. Meso compounds, we've done that, yeah. Finally, planes of symmetry. Warm-up page, let's go to that. Okay, we're kind of coming into where we're trying to pull everything together on stereochemistry. Any questions? Questions about stereochemistry? Yes.
Is there a way to determine R and S by looking at the Fischer projection instead of thinking about the wedge?
No, certainly. Certainly. I mean, the Fischer projection has a wedge dashed implied. I mean, if you want to do it over here, right, is this RS? And we did one earlier, whenever we had one in the plane. We did it in the Fischer projection. In the notes, we did this before. And this carbon, this one chiral carbon is RS. Well, what's high priority group on this carbon? Oxygen 1, then carbon or carbon. How do you break the tie? Well, what's this carbon bonded to?
2H.
It's bonded to O, H, and H. List the high priority group first. What's this carbon bonded to?
3 oxygens.
A double bond counts as if it's bonded twice. So it's bonded to O, and H. Well, what wins? Well, there's no winner there. So right here you get a winner. And this group is high priority. So this is 2, and this is 3, and the H is 4. But how is this, the low priority group is H here? Is it front or, how's it projected?
Forward.
Forward. So is this RS?
R.
It's R. Because it's counterclockwise, but the H is forward. So we just reverse it. Okay, this can help us pull things together a little bit. How many chiral carbons in Zocor? You have that one? Anybody? No more stereoisomers possible? Either of those drugs? Show this in a Fischer projection. R and S. Anybody have answers to any of these? All right, let's move down here then. Identify each of the following as chiral, achiral, or meso. First compound. Chiral, achiral, or meso. How do we want to approach this? We want to look for planes of symmetry. That's starting point. Where's Waldo? That will tell you the answer. Because if you find a plane of symmetry, the compound is achiral, meaning non-chiral. Okay, does this have a plane of symmetry? Right through here. Obviously not. 2 bromines on one side, not on the other? No. What about here, though? Is that a plane of symmetry? No, it's not. One bromine forward is not mirroring and bromine back. No plane of symmetry. This compound is chiral. If you drew the mirror image of that, it will be different. It will be the enantiomer. Can you draw the mirror image of this? Two ways to do it. You could actually draw it mirroring on your paper, or you could just change that to bold and this to dash. That would be the mirror image. What about this guy? What do you see here? Plane of symmetry. That's a plane of symmetry. Now, what's the answer? Chiral, achiral, or meso? It's certainly not chiral. But which one of those? Does it have chiral carbons? Yes, that carbon is chiral. That carbon is chiral. If you look at it, two chiral carbons. What do you want to call this compound? This compound is a meso compound because even though it has chiral carbons, it's not chiral as a whole. The mirror image is going to be the same thing. We know that because if you can find a mirror plane, trust me, got a mirror plane, the mirror image is going to be the same thing. All right, how about this one? That one should be easy. It's chiral. There's no mirror plane there. By the way, let's do R and S over here. Top carbon, bromine, top carbon's R. Pretty darn sure it is. So the bottom carbon is what? Real quick. What's the bottom carbon? S. If that's a mirror plane, it better be S. R is mirroring S. Okay? This is not a mirror plane, so this is probably both RR. Actually, both this is SS, because that's the same. That's SS. We know that's not a mirror plane because the mirror of S is not S. Chiral, I mean, that doesn't even have the same things. What about here? You got two carbons, and each carbon has the same things on it. Is that a mirror plane? I find it very hard to tell. I don't know. I want to first put it in a Fischer projection. Let's do this. Here the methyls are 4. Chlorine is like this. Let's call this chlorine 1 and this one 4. Chlorine at top and bottom here. With chlorine going away, what side's the methyl on? Chlorine going away, the methyl is on the right. The undrawn hydrogen is over here. With chlorine 4 going away, what side's the methyl on? On the right. Undrawn hydrogen here. Now we've done half the work. Now let's clear our mind. Now look at this structure. Where's Waldo? Right through there, you see? So much easier now. Since we found Waldo, what do we know about this compound? It's not chiral. But is it achiral or meso? This compound is meso because it does have chiral carbons. Two chiral carbons, yet it's not chiral as a whole.
Achiral means there's just no chiral carbon.
Achiral means not chiral. Meso is a special type of achiral. But if it's meso, we want to call it meso.
So what's the difference between?
Water would be called achiral. Ethanol, achiral. Compounds with chiral carbons that are not chiral get them a special name. See, these have chiral carbons, but they're not chiral, so that gets a special name. How about the next one? Why don't you work on those, because it really, you need to do it. How about something like this? Chiral, achiral, meso. We're basically playing Where's Waldo here. Okay? What do we see here?
No, it's achiral.
I see a plane of symmetry right through here. Half a chlorine mirroring half a chlorine, half a ring mirroring half a ring. Half a bromine going back, mirroring half a bromine going back. That's a plane of symmetry. What's the answer here? It's not chiral. Is it achiral or meso? It's achiral. Why? This compound doesn't even have chiral carbons. Is that carbon chiral? No, it's got a chlorine and H, but this and this is the same thing. Okay? It doesn't even have chiral carbons. So I'm just going to call it achiral, not chiral. How about this guy? I mean, obviously that's not a plane of symmetry, is it? Obviously that's not a plane of symmetry, right? How about right through here? You can cut through atoms. Is that a plane of symmetry? No. I don't see a plane of symmetry. This compound is chiral. And you should be able to draw an enantiomer of that. Now if I had put if you had a bromine here, now this is a plane of symmetry. We don't have that. It's chiral. Chiral. How about this one here? Well, this guy has two planes of symmetry. There's one right through here. There's also one right through there, right? It's doubly achiral. And it doesn't even have chiral carbons. That's not chiral. It's achiral. How about this one? Well, this one also has two planes of symmetry. That's a plane of symmetry. Methyl coming forward, mirroring a methyl coming forward. Half a bromine back, mirroring a half a bromine going back. But you also have a plane of symmetry. No, that's it. That's the only one. We have a plane of symmetry. We do have chiral carbons. This compound, those two carbons are chiral. And so this is meso, yeah? Okay, let's look at the other two. We need to be doing reactions like this at the bottom. I'm sorry I didn't get this passed out. Should have. We really don't need it today. I can pass it out next time. This is the alkyne handout. If you want to get one, you can pick one up on the way out. Upstairs tomorrow, guys. Have a good day.